Okay, we'll finish up by going over some last of the terminology and then showing how to calculate the atomic weight of an atom of the different isotopes. So we talked about the mass number, how to do some of these calculations, and then just a quick note about atomic symbols. This is some stuff that you have already probably intuitively figured out, but the first letter is always capitalized. If there is a second letter, it's always lowercase. And then for very rare cases, you can get up to 3 letters, but they're all the second and third letters are always lowercase. All right, molecules are different atoms that have been bonded together. It could be an atom with itself, kind of like the H2 here. We would call that a molecule, but it's still an elemental molecule. We could have, CO2 or H2O, but just different combinations of the different atoms with subscripts to tell you how many of the atoms are in that particular unit or that molecule. Subscripts tell you how many atoms are in a molecule of that particular type. They're on the lower right hand side. And again, if there's not one there, then it's just assumed to be 1. So here are 3 different isotopes of iodine. We would say iodine 121, iodine 122, and iodine 123. You can see the atomic number stays the same for all of them because that's elemental. And then we have different numbers of neutrons on these. So at least three different isotopes for iodine exist. And in chemistry, we really want to know the weight. And luckily, isotopes on Earth are in remarkably consistent percentages wherever you go. So that's going to allow us to calculate the average weight for the different isotopes that exist. So in this case, we can average these 3 guys with the percentages that they are and figure out the average weight. Okay. Using subscripts to count atoms, remember if you have a subscript, that tells you how many, but you can also have a subscript on the outside of a parentheses, and that'll tell you all of the things inside the parentheses are repeated however many times the subscript says. There's a little working on your own question there. The charge goes here. In this case, this is a triiodide ion, and it's weird. All of these things are acting together as a unit. So this unit is missing 1 electron. There are 3 total iodine atoms bonded together, and all 3 of them are just missing 1 electron. It doesn't mean that each atom is missing an electron, which would make 3 electrons missing. It just means for this total group. So the oxide ion has 1 atom of oxygen and 10 electrons. You should be able to write the symbol for that oxide ion. This is what we call a negative ion oxide, or it has an "ide" ending. You should be able to write that down. I'll leave that for you guys to figure out. Also, you should be able to figure out, based on this, the symbol for mercury 1 ion is Hg2+. How many electrons total does that mercury ion have? Remember, these electrons that are missing are on 2 different mercury atoms. Okay, so I'll let you guys work that out. Again, the mass number and atomic number, right? The atomic number is given, mass number is usually not. It's not really that useful for us in chemistry. It's useful in nuclear chemistry, but we don't normally deal with it in chemistry all that often. Okay. So just real quick, let me review this one. An isotope with 9 protons, 9 neutrons, and 10 electrons is used to image bone. So the way we can figure this out is first, we take the number of protons, and that's what determines the element. So given that, we can figure out what the symbol for that atom should be. If you go find the atomic number on your product table 9, you'll see that the symbol that corresponds to that is F. That's a fluorine atom. So we can write that. It has 9 neutrons and 10 electrons. So first thing you'll note is that we have an extra electron. So it's going to be a minus charge, and remember the charge goes in the upper right hand side. 9 is the atomic number, that goes in the lower left hand side, and then 9 neutrons, that is going to go into the mass number, which goes in the upper left hand side. Okay, so that's how we would write that symbol. We don't have to write any subscript on the lower right hand side because there's just 1 atom. Okay. We've already talked about what we're really interested in is the weight the average weight of the atoms when we're dealing with chemistry. And for that, isotopes present a problem. So I'm going to show you guys how we're going to calculate the atomic weight. This is a calculation that you need to know how to do for the class. And so first, this goes through a quick run through of the atomic mass units. If you're confused about that, make sure you go back to the book or pause the slide and get used to that. And when we're dealing with atomic weights, the number of isotopes is consistent throughout the Earth. Okay, and I mentioned that. So if you have a certain percentage in China, it's going to be the same as in the U.S. or wherever you go on Earth. We're going to have a way of calculating the averages. It's basically like what you guys are used to when you calculate an average, and I'll show you how it's related to that. But you have kind of a little bit more work to do to calculate this. So just to give you one really simple example, you have 3 different isotopes for carbon: carbon-12, carbon-13, and carbon-14. And we want to find the average of these. Well, when we find the average, we see that it's 12.01 atomic mass units. So the mass number here, 12, meaning in atomic mass units, this is basically going to weigh 12. This is basically going to weigh 13, and this one's basically going to weigh 14. Well, the average mass is just 12.01. So that tells you something about these percentages here, right? Carbon is mostly carbon-12. Okay. So how do we do that? Let me go ahead and run through how to do this calculation. And it's doing what's called a weighted average. The way we calculate a weighted average is you just need the abundance of the first species times the mass of that species added to the abundance times the mass of all subsequent guys. All right. And so if this were in chemistry, we're dealing with isotopes. So it would be the abundance of isotope 1 times the mass of isotope 1 plus the abundance of isotope 2 times the mass of isotope 2, etc. For each of the different isotopes we have. You could have 2, 3, 4, whatever. And let me show you guys an example. We'll work through this example and I'll illustrate how to do this calculation using that. So you're given here, this is kind of just a made-up example, but you have boron 10 and boron 11. All right, and then roughly speaking, boron 10 makes up 20% of the isotopes on Earth, and boron 11 80%. So we're going to need both of these numbers, the 10 and the 20%, and the 11, the mass number 11, and the 80%. So each of these masses, I don't want you to just use the mass number, but I'll give you the masses of these isotopes because they're not exactly the same for reasons which we'll talk a little bit more in detail later. But the masses for boron 10, just take it to be 10.0 for simplicity, and then the mass for boron 11 is just 11.0. Okay. So the way we would do this, if you can imagine it, let's just say assume there's 100 of them. All right. So then we have 20% are boron 10. So the way you would normally do this is you just add together all of the guys, in this case the masses, and then divide by the total number. Well, we assumed there was 100, so that the 20% would just make 20 of these, and the 80% would make 80 of these. So this is what you're kind of used to when you're calculating an average, and with some simple manipulation, this can be turned into the weighted average formula that we saw before. So how do you do that? Well, you can take these guys and multiply through by the denominator. Okay, so we're going to separate these two pieces by giving them both the denominator, and then we divide 20 by 100 to get a 0.2 and 80 by 100 to get 0.8. So then you just have 0.2 times 10 and 0.8 times 11. This is your weighting, right, or the abundance from the previous formula, and this is the mass. All right, so the abundance times the mass, and then you do that for each of the isotopes. When you do this, you get 10.8, so our weighted average, or what we're going to call the atomic weight, is 10.8 for boron. Okay. All right, so two different isotopes. You have the abundances of 20% and 80%, and then you plug them into that formula, and you get something that looks like this: abundance times mass plus abundance times mass, etc., for how many different isotopes you have. First thing to note is that this is not the same thing. If you're looking at it, right, it looks a little different than 20%. Remember, if you have a percentage, you need to divide by 100 in order to get the actual value for these operations. So you take the percentage, divide it by 100, and that'll turn it into a decimal, and that's what you use for the abundance. Okay, that's how you're going to need to do these calculations. This is a practice problem for you guys to work out, and you should pause it, figure out how to work it, and then I'll give you my answer here in just a second. Okay, so I've gone to a pencil and paper in my calculator and worked it all out just to give you the correct number. And when you're doing this, remember, you have a mass of 68.926 on this isotope, and then a percentage or abundance of 60.108%, but we need to divide that by 100. Sorry. And then we're going to add that to the multiplication of the mass here times the abundance here. Okay, this works out to be a little bit of an exercise in using significant figures. So what I got, hopefully you guys got the same thing, for this first one is 41.430. Okay, and the second one, all right, the second isotope is going to give us a contribution of 28.293. Okay, and then for the final value, I got the average weight. Right, the weighted average was 69.723. Okay. So all the sig figs should be correct on that. You got 5 sig figs here because you had 5 here and 5 here, and then same for this one. And then the addition and subtraction didn't change because we had the same number of decimals there. So you should have gotten 69.723. If not, shoot me an email and I'll go back and figure out what was going on there. And that is basically it. We'll go over the Bohr model real fast. The Bohr model is it's okay that it's not the most current understanding. It's really simple to explain, and it'll help you understand the difference between valence and core electrons. And so picture here we have an atom's nucleus. There are these shells where electrons are going to live. Okay, and each of these shells can hold a different number of electrons. This first shell can hold 2 electrons, and that's it. The second shell can hold 8, and each subsequent shell can hold more and more electrons. You picture the houses are getting bigger so they can hold more and more electrons in there. And our electrons need a home. All right, so this first shell, you're going to fill that up before going on to filling up the next shell, at least for the ground state, which is the most important one. Right? Everybody kind of wants to get down to the ground state. So if you had, say, an atom of lithium, all right, if you look at your periodic table, the atomic number is 3. That means for a neutral atom, we need 3 electrons in there. That means you're going to have 2 electrons here, and you're going to have 1 electron in the second shell. So when we move on to the next shell, all right, everything in the completely filled inner shell is then a core electron. So then valence electrons are the ones that are in the shell that we're filling up. For lithium, we only had 1 electron in this shell, so that means we only had 1 valence electron, and that was in the shell number 2 here. All right, so I can put 7 more electrons in here, but for now I just have 1. So there you go. The difference between your valence and core electrons are the shell that you're filling up in this simple Bohr model are the valence electrons. And remember, we're usually dealing with neutral atoms, and so the number of electrons just equals the atomic number of the number of protons. So the Bohr model is a nice simple one. It really will help you understand a lot of the different concepts. Electrons have to live in these shells, and each of these shells has a different energy. And so when it jumps, let's say we had helium, so it has 2 electrons here and that's it. I could take one of these electrons and bump it higher in energy, and it can go to the second or the third or the fourth shell. But if it goes between the first and the second shells, then it's a certain specific jump in energy because each of these shells has a specific energy associated with it. All right. So that almost gets you to the modern view of electrons, and that's okay. That's all we really need for this particular class. And then you have a nice little summary table from the book here. As our understanding of the atom and the nucleus and the subatomic particles got better and better. You see there's still a space here to get to the more modern one, but we don't need it for this class. And so Dalton's atomic theory, we thought that these guys were just like, solid balls, all right? And then we had a further refinement with the plum pudding model, and we figured out that there are positive and negative charges, and we thought that the negative charges were like little, the plums in the plum pudding, and then the positive was this matrix of pudding. And then we further refined that because we knew that there was a nucleus, and we also figured out that these electrons had energy, certain specific energy levels, and we postulated they have these shells. All right, that's the Bohr model. All right, that does it for this chapter. And remember, spend some time reading it, work some problems, do your homework, and then you should have this chapter down. If you have any questions or anything, just shoot me an email, and then we can talk about it in office hours or something. Okay, good luck.